Have you ever paused to truly consider the invisible symphony happening inside your computer? Making sense of the chaos when you're juggling like a dozen browser tabs, streaming music, maybe even compiling code.
Mm-hmm.
It feels like magic, doesn't it?
Hmm.
Everything just works.
It really
But
does.
behind that seamless experience,
Mhm.
there's a master conductor,
Yeah,
orchestrating every single digital instrument, ensuring harmony and responsiveness.
that's exactly right. And that conductor, that's what we call CPU scheduling. It's this utterly essential, though often completely invisible, mechanism that lets your computer manage countless tasks.
Right.
It's the reason you perceive everything is running simultaneously, even when fundamentally your CPU can only execute one instruction at a time, well, per core.
Yeah, exactly. Today, we're taking a deep dive into CPU scheduling. We'll explore its foundational concepts, the ingenious algorithms that underpin it, and the advanced techniques that keep our modern operating systems humming along. Our mission for you, our curious listener, is to not only understand what CPU scheduling is, but to really uncover why it matters. And, arm you with those surprising insights and aha moments that'll make you feel truly well-informed.
Get you up to speed.
Think of it as a shortcut, maybe, to mastering how your computer's brain choreographs its most complex dances. Let's unpack this. So for those of us who appreciate the intricate workings under the hood, let's kind of set the stage. What is CPU scheduling in the grand architecture of an operating system, and, well, why is it so fundamental?
Okay. So at its heart, CPU scheduling is the operating system's pivotal decision-making process. It's all about allocating the central processing unit, the CPU, that core brain of your computer, to different tasks.
Okay.
We usually call these tasks processes, or sometimes threads. It's about distributing that incredibly valuable processing time fairly and efficiently over time.
Right.
And this becomes especially critical in time-shared operating systems, like the one you're undoubtedly using right now, whether it's Windows, Mac OS, or Linux.
Yeah, pretty much all of them now.
Exactly. These systems create the illusion of concurrent execution by rapidly switching between numerous users or applications. Without robust CPU scheduling, your computer wouldn't just be sluggish, it would be practically unusable for multitasking.
It sounds like this intricate ballet, almost like a carefully choreographed dance between a program's intense computational needs and maybe its more relaxed moments spent waiting for data. Can you elaborate on that dance, those different bursts of activity?
That's actually an excellent way to put it. Most processes don't just hog the CPU continuously. They alternate between two fundamental types of activity. We call them CPU bursts and I/O bursts.
Okay, CPU and I/O.
Right. A CPU burst is when a process needs to do intensive calculations, think rendering complex graphics, encoding a video, compiling code. It's actively consuming CPU cycles.
Makes sense.
An I/O burst, on the other hand, is when the process is waiting. It's waiting for something from an input-output device, maybe data from a disk, a packet over the network, or even just for you to type something. Ah, okay. So waiting for the slow stuff, relatively speaking.
Precisely. Our source material, specifically figure 6.1, it beautifully illustrates this alternating sequence, showing how processes just switch back and forth between these two states.
And here's where the clever engineering really shines, I imagine. If a process goes into an I/O burst, waiting for that slow disk or network, the CPU isn't just sitting idle, right? Tapping its digital foot. That sounds like a colossal waste.
Exactly right. That would be incredibly inefficient. And this is one of the foundational insights into good OS design. When a process initiates an I/O operation and has to wait, the operating system doesn't let the CPU just pause.
No waiting around.
Nope. Instead, the scheduler springs into action. It rapidly switches the CPU to another process that is ready to run, one that needs calculations done now.
Gotcha. Keep it busy.
This maximizes the utilization of that incredibly expensive CPU. It's this rapid, almost imperceptible switching that creates that smooth illusion of seamless multitasking. It's really the core reason your computer can appear to be doing many things at once. So these decisions to switch processes, they aren't random, obviously. They must happen at very specific, predictable points in a process's journey through the system. When are those critical moments? When does the scheduler actually step in?
You're right, they're not arbitrary at all. Scheduling decisions are triggered at 4 key moments in a process's life cycle. First, when a process transitions from a running state to a waiting state, like if it issues an I/O request and has to pause, or maybe it waits for a child process to finish up.
Okay, so if it needs to wait for something external.
Exactly. Second, when a process moves from running back to the ready state, this typically happens because of an interrupt, like a timer interrupt saying, hey, your time slice is up.
Ah, the timer tick.
Right. Third, when a process switches from a waiting state back to ready, this means the I/O operation it was waiting for has finally completed and it's now able to run on the CPU again.
So the data arrived, or the keyboard input happened.
Precisely.
Yeah.
And finally, a scheduling decision must be made when a process terminates, finishes its job completely, freeing up the CPU.
Okay, those make sense. But it sounds like there's a fork in the road for the OS in some of those scenarios. For the first and last points going to wait or terminating, it seems like there's no choice, right? The CPU has to be reallocated.
This is a very astute observation.
But what about the other two? When an interrupt happens, or I/O completes, did the OS always take the CPU away then?
That leads us right to the crucial distinction between preemptive and non-preemptive scheduling. You're spot on about the first and fourth scenarios, a process going into wait or terminating. In those cases, the OS must select a new process to run if one is ready. No choice.
Right.
However, for the second and third scenarios, running to ready via interrupt or waiting to ready via I/O completion, the operating system can choose. In preemptive scheduling, the OS can, and usually does, take the CPU away from a currently running process, even if that process hasn't finished its CPU burst.
Ah, okay. It interrupts it.
Yes. This is the dominant approach in modern general-purpose OSISes like Windows, Linux, Mac OS. It allows for much better responsiveness and fairer resource distribution.
Makes sense for interactive stuff.
Exactly. In contrast, non-preemptive scheduling means that once a process starts executing, it continues until it voluntarily gives up the CPU, either by finishing its burst, making an I/O request, or terminating.
So it runs until it stops itself.
Pretty much. It's simpler to implement, but generally unsuitable for the interactive systems we use daily because one long process could just freeze everything else out.
Right, that unresponsiveness issue again. Okay, so the scheduler makes the high-level decision, process B runs next. But then something else has to physically make that switch, right? Is there a dedicated component for that heavy lifting?
Absolutely. Once the CPU scheduler makes its decision, selecting which process gets the CPU next, a specialized, low-level component called the dispatcher takes over.
The dispatcher.
Think of the dispatcher as the hands-on executive who actually implements the scheduler's orders. Its primary job is to give control of the CPU to the process selected by the scheduler. This involves 3 key steps. 1, context switching. This is super critical. It means saving the current state of the process that's leaving the CPU all its registers, program counter, stack pointer, memory info, and then loading the saved state of the new process that's about to run.
Like hitting pause on one movie and instantly loading the exact frame of another. That sounds expensive.
It is, relatively speaking. 2, switching to user mode. The CPU needs to shift from the privileged kernel mode, where the OS runs, to the less privileged user mode, where the application code runs. And 3, jumping to the program's start point. The dispatcher then jumps to the appropriate location in the new program's code to resume its execution right where it left off, or at the beginning if it's new.
That sounds like a lot of delicate work for the dispatcher. And if this context switching happens constantly, especially in a busy system, couldn't that overhead itself become a bottleneck? Is there a metric for how long that switch takes?
You've hit on a critical engineering concern. Yes, there is. The time it takes for the dispatcher to perform this entire switch from halting one process to starting another is called dispatch latency.
Dispatch latency. Got it.
Minimizing this latency is absolutely crucial for the overall responsiveness of a system, especially in real-time systems where deadlines are super strict, like in industrial controls or medical equipment. Every microsecond counts.
Because it's pure overhead, right? No useful work is getting done during the switch itself.
Exactly. A high dispatch latency means delays, making the system feel slow, or, in those critical applications, potentially causing catastrophic failures. OS designers strive to make context switching and dispatch latency as absolutely minimal as possible.
Okay, so if the operating system is constantly making these intricate decisions about who gets the CPU, how do we, or maybe how do the OS designers, know if it's doing a good job? What's on the report card for a CPU scheduler? What are we measuring?
That's an excellent question, and it immediately highlights the inherent trade-offs in system design. There's really no single best scheduler. The optimal choice always depends on the specific goals and workload of the system.
Ah, the classic engineering answer. It depends.
Pretty much. We evaluate schedulers based on several key criteria, and very often optimizing for one metric means compromising on another. It's a constant balancing act.
Okay, so what are these criteria?
Well, first, there's CPU utilization. This is perhaps the most straightforward. We want to keep the CPU as busy as possible doing useful work. Ideally, in a heavily loaded system, we're aiming for utilization somewhere between, say, 40% and 90%. Too low means wasted power.
Makes sense. Keep the expensive part busy.
Right. Then there's throughput. This measures the number of processes completed per unit of time. For batch systems, or any system handling lots of distinct tasks, higher throughput means more work gets done overall.
More jobs finished per hour, basically.
Exactly. Next up is turnaround time. This is the total time a process takes from the moment it's submitted to the system until it completely finishes execution. It includes all the time spent waiting to get on the CPU, waiting for I/O, plus the actual execution time.
So from start to absolute finish for a single task.
Correct. And related, but distinct, is waiting time. This metric specifically focuses only on the total time a process spends waiting in the ready queue, just sitting idle, ready to run, but not running on the CPU. Minimizing this is often a direct goal of many algorithms.
Okay, so how long is just twiddling its thumbs waiting for the CPU?
Precisely. And finally, arguably the most crucial for the systems we use daily is response time. For interactive systems, this is key. It's the time from when a request is submitted, like you click a button or type a character, until the first response is produced.
Not the whole task, just the first sign of life.
Exactly. It's about how quickly the user feels something is happening, even if the whole complex task isn't done yet. A fast response time makes a system feel snappy, immediate, responsive. That's critical for a good user experience.
It really does sound like a complex balancing act where the best scheduler is highly context dependent. You simply can't max out one metric without impacting the others, can you?
Almost never.
Like a scheduler that maximizes CPU utilization for huge background tasks might make your web browser feel terribly sluggish,
Right.
while one optimized only for lightning-fast response times might not get as many big batch jobs done efficiently in the long run. It's all about finding that precise compromise for the system's intended purpose.
That's the art of scheduler design, absolutely.
Mhm.
Okay, so with those metrics, utilization, throughput, turnaround, waiting, response time in mind, let's dive into some of the most fundamental algorithms. These aren't just, historical footnotes. They form the bedrock of almost all modern scheduling logic, even in the really complex systems we use today.
All right, first up. First come, first served, or FCFS. This one sounds incredibly intuitive, almost like waiting in line at a coffee shop or a grocery store checkout. First person in line gets served first. Simple, seems fair, easy to grasp, right?
Exactly. FCFS is indeed the simplest algorithm to understand and implement. It processes tasks strictly in the order they arrive in the ready queue, just like that coffee shop line.
Okay.
And it's also inherently non-preemptive. Remember what that means. Once a process begins executing on the CPU, it continues to run without interruption until it either completes its current CPU burst or it makes an I/O request and voluntarily gives up the CPU.
Right. No interruptions. Runs till it stops itself.
Great.
But I'm already anticipating a potential pitfall here, thinking about that coffee line again.
Mm-hmm.
If someone at the front orders an incredibly complex, multi-step latte extravaganza, everyone behind them just wanting a quick black coffee is going to be delayed quite a bit, right?
Yeah.
This sounds like it could lead to some significant inefficiencies.
You're anticipating the primary design flaw of FCFS perfectly. It's famously known as the convoy effect.
The convoy effect.
Okay. This happens when a series of processes, especially shorter, maybe I/O-bound ones, get stuck waiting behind a very long CPU-bound process. Imagine a few short tasks arrive, but one really long one got on the CPU first.
Yeah.
All those shorter processes are then delayed, sometimes significantly, even if they only needed a tiny slice of CPU time. This can drastically reduce overall CPU utilization because other processes might be ready but can't run, and definitely increases the average waiting times. The CPU might even sit idle later if the long process goes into I/O and the short one's already finished.
Right, the whole convoy gets held up by the slow one at the front.
Precisely. Let's illustrate this with a concrete example, kind of like the ones in our source material. Imagine 4 processes arriving at slightly different times, each needing a specific CPU burst. P1 needs 8 milliseconds of CPU, arrives at time 0. P2 needs 4 milliseconds, arrives at time 1. P3 needs 9 milliseconds, arrives at time 2. P4 needs 5 milliseconds, arrives at time 3.
Okay, got the setup. P1 arrays first.
Right. So in an FCFS schedule, the timeline would look like this. P1 starts at time 0, runs for 8 meters, finishing at time 8. P2 arrives at time 1 but has to wait for P1. It finally starts at time 8, runs for 4 meters, finishing at time 12.
Ouch, waited 7 meters already.
P3 arrives at time 2, waits for P1 and P2, starts at time 12, runs for 9 meters, finishing at time 21.
Waited 10 meters.
And P4 arrives at time 3, waits for P1, P2, and P3. Starts at time 21, runs for 5 meters, finishing at time 26.
Wow, waited 18 meters for a 5 meters job. That feels inefficient.
It really is. Now, let's quickly calculate those waiting times. P1 waits 0 meters. P2 waits, start time 8, arrival time 1, equals 7 meters. P3 waits, start time 12, arrival time 2, 35 meters. P4 waits, start time 21, arrival time 3, equals 18 meters. The total waiting time is 0 plus 7 plus 10 plus 18 plus 35 meters. So the average waiting time for these 4 processes is 35 divided by 4, which is 8.75 milliseconds.
8.75 meters average. Wait.
As our source material points out in similar examples, more sophisticated algorithms can achieve significantly lower average waiting times, clearly showing the disadvantage of FCFS in these kinds of mixed job scenarios.
Okay, so if FCFS is simple, but suffers from that crippling convoy effect, what if we could be a bit more strategic, maybe rearrange the line? What's the optimal approach if we could somehow magically predict the future?
If we possessed perfect foresight, the shortest job first SJF algorithm would be our undisputed champion. It is actually provably optimal in terms of providing the minimum possible average waiting time for a given set of processes.
Provably optimal. That sounds impressive. What's the logic?
The logic is quite compelling. SJF always picks the process with the smallest next CPU burst to run. By quickly completing the shorter jobs first, SJF minimizes the time that many other processes spend waiting in the queue. This leads to a much lower average waiting time across the entire system compared to FCFS.
Okay, get the quick ones out of the way first. Seems smart.
It is. However, and this is the significant catch that makes perfect SJF difficult, maybe impossible in practice. How do you know the length of the next CPU burst before it actually happens?
Right. Crystal ball problem.
Exactly. In a real dynamic system, you simply can't know for sure. The best we can do is estimate the length of the next CPU burst. Operating systems often do this by looking at a weighted average of the process's previous burst lengths, using techniques like exponential averaging.
So it's based on past behavior, hoping the future looks similar.
Precisely. So, while theoretically optimal, perfect SJF remains more of an ideal benchmark rather than a universally implementable algorithm in its purest form.
That makes perfect sense. It's like trying to guess exactly how long someone will take at the coffee counter before they even order. You can make an educated guess based on their usual order, but you never truly know. But I've heard there's a variation, a preemptive version, that attempts to make SJF more dynamic and responsive. How's that work?
Indeed there is, and it's where SJF becomes much more practical and powerful in real systems. There's a preemptive version called shortest remaining time first, SRTF.
Shortest remaining time first.
Okay. This is where the magic of preemption really comes into play. With SRTF, if a new process arrives in the ready queue, the system looks at its required CPU burst time. If that time is shorter than the remaining time needed by the process currently executing, the running process is immediately preempted.
So it gets kicked off the CPU.
Yep, temporarily. The CPU is then swiftly given to the newly arrived shorter job. This dynamic preemption helps to keep the average waiting time even lower than non-preemptive SJF and makes the system incredibly responsive to short, urgent tasks that might pop up.
Okay, that sounds much more reactive. Can we revisit our P1, P2, P3, P4 example to see how SRTF would change things? I think the source had a diagram like figure 6.4 for this.
Absolutely. Let's trace it using SRTF. Remember, P1, 8 meters burst, arrives at time 0, P2, 4 meters burst, arrives at time 1, P3, 9 meters burst, arrives at time 2, P4, 5 meters burst, arrives at time 3. Here's the SRTF timeline. Time 0, P1 starts, it's the only one, remaining burst, 8 meters. Time 1, P2 arrives, needs 4 meters. We look at P1, it has 7 meters remaining, 8-1. Since P2's 4 meters is less than P1's remaining 7 meters, P1 is preempted. P2 starts running.
Wow, okay. P1 gets interrupted after just 1 meters.
Time 1 to 5, P2 runs for its full 4 meters burst. It finishes at time 5. During P2's run, P3 arrived at time 2, needs 9 meters, and P4 arrived at time 3, needs 5 meters. Time 5. P2 finishes. Now, who's in the ready queue? We have P1, 7 meters remaining, P3, 9 meters needed, and P4, 5 meters needed. The shortest remaining time is P4's 5 meters, so P4 starts.
Okay, P4 jumps ahead of P1 now.
Time 5 to 10. P4 runs for its 5 meters burst, finishing at time 10. Time 10, P4 finishes. Ready queue now has P1, still 7 meters remaining, and P3, 9 meters needed. Shortest is P1, so P1 resumes.
Finally, P1 gets back on.
time 10 to 17. T1 runs for its remaining 7 meters, finishing its total 8 meters berthed at time 17. Time 17, P1 finishes. Only P3, 9 meters needed remain. So P3 starts. Time 17 to 26, P3 runs for its 9 meters, finishing at time 26. Everyone's done.
That schedule looks totally different, much more jumping around. What does that do to the average waiting time compared to FCFS's 8.75 meters? The source mentioned 6.5 meters for a similar SRTF case.
Let's calculate it carefully based on when they could have run versus when they did. P1 arrived 0, ran 0-1, waited 110, ran 10-17, total weight 1-1 plus 10-1 equals 9 meters. Let's rethink. Waiting is time spent ready but not running. P1 was ready at 0, ran 0-1, preempted, ready again at 1, waited until 10. So wait, 10-1, 9 meters. P2 arrived 1, ran 1-5, wait 0-5, wait to 0 meters. T3 arrived 2, waited until 17, ran 17-26, waited 17-2. P4 arrived 3, waited until 5, ran 5-10, wait 5-3, doubly 2 meters. Total waiting time 9 plus 0 plus 15 plus 2 plus 26 meters. Average length of 26.4 equals 6.5 milliseconds.
6.5 meters. That's a definite improvement over FCFS's 8.75 meter. So that preemption really helps chop down the waiting.
Exactly. The SRTF example clearly demonstrates how preempting longer jaws for shorter arriving ones consistently creates a more dynamic schedule with a significantly lower average waiting time, highlighting its efficiency even if it requires more context switches.
Okay, so we've looked at arrival order, FCFS, and predicted length, JF, SRTF. But what if some tasks are just inherently more important than others? You wouldn't want a critical system monitor task to wait patiently behind, say, a game downloader, right? Is there a way to encode that kind of importance directly into the scheduling decision?
That's precisely where priority scheduling comes into play. It's a very fundamental concept. Each process is assigned a priority number, often an integer. The rule is simple. The CPU is always allocated to the process with the highest priority that is currently ready to run.
Highest priority wins.
Right. Now, conventions vary. Sometimes lower numbers mean higher priority, like 0 being the highest. Sometimes higher numbers mean higher priority. You just need to know the system's convention.
Okay.
For instance, a critical system process like a network driver might have priority 0, highest, while your web browser might be priority 10, and a background backup job might be way down at priority 20, lowest. The scheduler will always pick the task with the best priority number that's ready.
And you mentioned SJF is related.
Yeah, interestingly, SJF can be seen as a special case of priority scheduling. The priority is just inversely proportional to the predicted length of the next CPU burst. Shorter predicted burst implies higher priority.
So it's about giving the VIPs of the computer world preferential treatment. That seems logical for certain tasks, but I can already foresee a potential drawback, especially for those tasks stuck at the bottom of the priority ladder. What happens to them?
You're anticipating the primary issue with simple priority scheduling, starvation, or as it's sometimes called, indefinite blocking.
Starvation. Sounds bad.
It is. A low priority process might literally never get to run if there's a continuous stream of higher priority processes entering the ready queue. Imagine that background backup job at priority 20. If new interactive tasks, priority 10, system updates, priority 5, and other high-priority processes keep arriving, the backup might perpetually be denied CPU time. It just keeps getting pushed to the back of the line.
So it just starves for CPU time. That's obviously not good. How do systems prevent that?
The common and effective solution is a technique called aging.
Aging, like getting older.
Sort of. Aging is a mechanism where a process's priority gradually increases the longer it waits in the ready queue without running. So even that lowest priority backup job, if it sits waiting long enough, its priority will slowly creep up, maybe from 20 to 19, then 18, and so on.
It gets more important the longer it waits.
Exactly. This ensures that over time, even the lowest priority process will eventually accumulate enough priority to reach a level high enough to get a turn on the CPU. It guarantees progress for all tasks and prevents that indefinite blocking or starvation. It's a pragmatic way to combine the benefits of priority scheduling with fairness.
Okay, we've covered some real foundational concepts, FCFS, SJF, priority. Moving beyond those basics, how do modern operating systems manage the incredible demands of, multiple users, highly interactive applications where quick responsiveness is absolutely paramount? Those simpler, maybe non-preemptive methods certainly wouldn't cut it today.
No, definitely not. This leads us naturally into algorithms specifically designed for more dynamic, time-sharing, and interactive computing environments. These often build upon the principles we've just discussed, but add layers of sophistication to handle the complex, real-world demands of the systems we use every day.
Round robin. Now, that's a name many people are familiar with, even if they don't know the specifics. It's almost synonymous with the whole idea of time sharing, isn't it? Feels like a real classic.
Absolutely. Round robin, or RR, is indeed a cornerstone of time-sharing systems. It was famously pioneered by systems like CTSS, the compatible time-sharing system, way back in the early 1960s.
Wow, that
Oh,
early.
yeah. RR is fundamentally a preemptive algorithm. It doesn't let any single process monopolize the CPU. Instead, each process gets a small, fixed unit of CPU time. We call this a time quantum or a time slice.
Time quantum. Okay,
Yeah.
how long is that usually?
Typically quite short, maybe in the range of 10 to 100 milliseconds in modern systems. Now, if a process hasn't finished its current CPU burst by the end of its time quantum, the operating system immediately preempts it, pulls it off the CPU.
Okay, forces it off.
Yeah, and then it's placed back at the end of the ready queue to await its next turn. This rapid cycling through all the ready processes gives that illusion of simultaneous execution and, crucially, provides pretty good responsiveness for interactive users because no one has to wait too long for their next little slice of time.
So it's like a digital game of musical chairs, kind of. Everyone gets a short turn, then the music stops, timer interrupt goes off, and you wait for your next go-around. That time quantum sounds like a really critical parameter to tune correctly. What happens if you set it too long or maybe too short?
You've hit on the most critical design challenge for round robin. The length of the time quantum is incredibly sensitive and directly impacts performance in a couple of ways. If the time quantum is too large, RR essentially degenerates into just being first come, first served, FCFS.
Oh.
Well, if the quantum is very long, most processes might complete their entire CPU burst within a single quantum anyway. There'd be no need for preemption based on the timer. This can reintroduce that dreaded convoy effect for short tasks stuck behind long ones, which hurts responsiveness.
Okay. Too long is like FCFS again. What about too short?
Conversely, if the time quantum is too small, the system starts spending an excessive amount of its time on context switching rather than actually doing useful application work. Remember, context switching is pure overhead.
Right, the time-wasted switching between tasks.
Exactly. For instance, if the context switch time is, say, 1 millisecond, and your time quantum is only 10 milliseconds, then 10 plus 1, or roughly 10% of the CPU's valuable time, is wasted just shuffling tasks around. That leads to poor overall CPU utilization and throughput.
So you need a balance. Large enough to minimize switching overhead, but small enough for good response time.
Precisely. Finding that sweet spot for the time quantum is a delicate art in OS tuning. It often depends heavily on the typical workload. Let's illustrate this trade-off. Imagine 3 processes, P1, P2, and P3, each needing a 10-time unit CPU burst, and they all arrive at time 0. If the time quantum is just 1 time unit, the scheduler would cycle P1, P2, P3, P1, P2, P3 10 times each until they finish. P1 runs 0, 1, P2 runs 1, 2, P3 runs 2, 3, P1 runs 3, 4, and so on. The average turnaround time would be relatively high. The source suggests around 29 units for a similar case. Why? Because each process gets interrupted many times and has to wait for everyone else to get their turn repeatedly.
It's lots of waiting in the queue.
However, if the time quantum is 10 time units, equal to their burst length, P1 runs for 10 units from time 0 to 10 and finishes. P3 runs for 10 units from time 20 to 30 and finishes. In this scenario, each process gets to run for its entire burst without any timer preemption. It behaves just like FCFS. The average turnaround time drops significantly, maybe down to 20 units.
Because fewer context switches and less waiting for others within its own burst.
Exactly. This shows how a larger quantum, allowing processes to often finish their bursts in one go, can drastically improve turnaround time by reducing the number of context switches. But if P1 needed 11 units, it would be preempted at 10, letting P2 run, maintaining some responsiveness. It's always that trade-off. Hashtag multi-level queue scheduling.
Okay, round robin is good for general time sharing. But what if you have dramatically different types of processes running? Say, some highly interactive ones, like a video game or maybe a text editor where you want instant feedback, and then some long-running, non-urgent batch jobs, like a nightly data analysis script. Would you really want to schedule them all together in the same single queue, using the same round-robin rules? Seems inefficient for the batch jobs, maybe.
Absolutely not. That's precisely the challenge that multi-level queue scheduling aims to solve. This approach tackles that system diversity by partitioning the single ready queue into several separate, distinct queues.
Okay, multiple queues.
Right. Each queue is often designed for a specific class or type of process, effectively segregating the different workloads. For example, you might commonly have a foreground queue for interactive processes, like your video game, shell sessions, text editor, where quick response time is the absolute top priority. A background queue for batch processes, like that data analysis script, a large file compression, a long compilation, where overall throughput and turnaround time are more important than immediate responsiveness.
So you separate them based on their needs, interactive versus batch.
Exactly. And the real power and flexibility here come from the ability to assign different scheduling algorithms to different queues. So the foreground queue might employ round robin with a short time quantum to ensure that snappy responsiveness,
Okay.
while the background queue might use a simpler first come, first served FCFS algorithm, since the exact order they finish might not matter as much as just getting them all done eventually. Or maybe RR with a much larger quantum.
So once you have these separate queues, each with its own internal rules, how does the operating system decide which queue to pull the next process from? Is there like a master scheduler overseeing these different queues?
Exactly. There's an overarching scheduler that manages the interaction between these queues. This is often implemented using a fixed priority preemptive scheme.
Okay, priorities between the queues themselves.
Right. For instance, all processes in the foreground queue might consistently have a higher priority than any process in the background queue. If a foreground process becomes ready, say you hit a key in your editor, it can immediately preempt a background process that might be currently running. The background job gets paused, the foreground job runs.
Oh, so foreground always interrupts background.
Typically, yes. However, this hierarchical priority system brings back a familiar problem we discussed earlier with priority scheduling in general.
Let me guess. Starvation.
You got it. Starvation. The lower priority queue or background queue, for example, could potentially suffer from starvation if there's just a continuous stream of processes arriving in the higher priority foreground queue. The background jobs might never get a chance to run.
Right. So how do they fix that here? Aging again?
Aging is one way. Another common technique is to give the lower priority queues some guaranteed percentage of the total CPU time. Maybe the foreground queue gets 80% of the CPU, and the background queue is guaranteed at least 20%, using round robin between the queues themselves based on these percentages. This prevents total starvation while still heavily favoring the interactive tasks. #tag multi-level feedback queue scheduling.
This sounds like we're building up layers of complexity. Multi-level queues are better than one queue, but still have potential issues like starvation or maybe miscategorizing a process. What if a process starts behaving like an interactive task, needing quick responses, but then suddenly turns into a CPU hog for a while? Can the system adjust dynamically?
That's an astute question, and it leads us directly to the multi-level feedback queue scheduling algorithm. This is generally considered the most general, flexible, and powerful scheduling algorithm, and it's often the basis for how real-world operating systems like Linux and Windows actually manage their incredibly diverse workloads.
Feedback queue. Okay, what's the feedback part?
The key innovation here is that it allows processes to move between the different queues based on their observed behavior or age. That's the feedback loop. This adaptiveness makes it incredibly powerful.
So a process isn't stuck in the interactive or batch queue forever.
Exactly. For instance, imagine a system with 3 queues. Q0, highest priority, shortest quantum, maybe for very interactive tasks. Q1, medium priority, medium quantum. And Q2, lowest priority, longest quantum, or FCFS, for batch-like tasks. Now, if a process in Q0 uses up its entire short-time quantum without blocking for I/O, that might be a signal that it's becoming more CPU-bound. So the scheduler could automatically demote it down to Q1.
Okay, it moves down a level.
Right. If it then uses up its entire medium quantum in Q1, it might get demoted again to Q2.
So CPU hogs drift downwards.
Precisely. Conversely, if a process has been waiting for a very long time down in a low-priority queue like Q2, the scheduler might promote it back up to a higher queue, say Q1. This effectively implements that aging mechanism we talked about and prevents starvation.
Okay. So it can move up and down based on behavior and waiting time. That sounds incredibly dynamic and responsive.
Yeah.
A process's actual behavior on the fly dictates its priority and even the scheduling algorithm it's subjected to, rather than being stuck with a fixed type assigned at the beginning.
That's the beauty of it. This flexibility allows operating system designers to finely tune the scheduler for specific workloads and adapt to changing system conditions. The exact definition and configuration of such a scheduler are highly customizable. You need to define several key parameters. 1, the number of queues. Could be 3, could be 10, could be dozens. 2, the scheduling algorithm for each queue, R with different quanta, FCFS, etc. 3, the method for determining when to promote a process, arrangee, based on waiting time. 4, the method for determining when to demote a process, for example, based on CPU usage within a quantum. 5, and how to initially place a process into a queue when it first enters the system, for example, do all new processes start at the top.
Wow, that's a lot of tuning knobs.
It is, but that configurability is what makes it so powerful. And this robust flexibility isn't just theoretical. As mentioned before, even influential early time-sharing systems like CTSS back in the 60s employed a form of multi-level feedback queue. It gave programs shorter quanta at higher priority levels and would demote them if they didn't finish quickly, demonstrating its effectiveness even in the earliest days of modern interactive computing.
Okay, we've spent a good deal of time discussing processes as
Mhm.
these kind of big units of work that the CPU scheduler manages. But modern operating systems are also teaming with threads, which seem to be smaller, more nimble components within a process. How does this distinction, processes versus threads, change the scheduling game? Does the CPU schedule threads or processes or both somehow?
That's a crucial distinction, you're right. And understanding it is absolutely key to grasping how modern concurrency actually operates under the hood. While a process is indeed the fundamental unit of resource ownership and executing program with its own dedicated memory space, file handles, etc., it can also contain multiple threads of control. Think of a modern web browser. The entire application runs as one process, typically. But individual tabs, or maybe separate tasks within a tab like fetching images, running JavaScript, playing media, these might execute as distinct threads within that single browser process.
Ah, so multiple streams of execution inside one program.
Exactly. This allows for much finer-grained concurrency. Different parts of the same program can execute seemingly in parallel, sharing the process's resources like memory, which is more efficient than starting whole separate processes for each little task. Now, the answer to whether the CPU scheduler directly schedules threads of processes depends critically on the specifics of how threads are implemented in the OS, particularly what we call the contention scope. Hashtag contention scope. There are two primary types of contention scope, which basically define where threads compete with each other for CPU time. Process contention scope, PCS. This model primarily applies when you're dealing with user-level threads. In PCS, the competition for the CPU happens only among threads belonging to the same single process.
So threads in Firefox only compete with other Firefox threads.
Under PCS, yes, conceptually. The user-level thread library, which is part of the application, or a runtime library, not the OS kernel itself, schedules these user threads onto a pool of available lightweight processes, LWPs. An LWP is sort of a virtual processor provided by the kernel to the process. The kernel schedules the LWPs onto the physical CPUs, but it doesn't see the individual user threads directly.
So there's an extra layer of scheduling done by the application's library.
Right, it's a many-to-many or many-to-one mapping of user threads to LWPs. System Contention Scope, SCS. This model applies directly when using kernel-level threads. Here, the competition for the CPU takes place among all threads in the entire system, regardless of which process they belong to.
Ah, so all threads from all applications compete globally.
Exactly. The operating system's kernel makes these scheduling decisions directly and globally, much like it schedules processes, which can be thought of as processes with just one thread. The kernel sees every single kernel thread as an independent schedulable entity.
So if a system uses kernel-level threads, the kernel itself is managing all those individual threads across the entire system. That sounds like a much more direct and maybe more efficient way for the OS to handle concurrency. It means the kernel has the complete picture, right? No hidden user threads.
You're absolutely right. And here's a really critical insight for understanding modern systems. In operating systems that utilize the one-to-one threading model, and this includes the big ones like Windows, Linux, and recent versions of Solaris, each user thread that gets created maps directly and explicitly to one distinct kernel thread.
One user thread equals one kernel thread. Simple.
Yep, a one-to-one mapping. And the implication of this is huge for scheduling. For these predominant operating systems, scheduling only uses System Contention Scope, SCS.
Why only SCS?
Because the kernel is directly managing all active threads on the CPU. There's no separate user-level thread library trying to multiplex many user threads onto a smaller number of kernel entities, LWPs. Every thread you create, whether implicitly by your programming language's runtime or explicitly in your code, becomes a first-class kernel schedulable entity.
So the kernel scheduler just sees a big pool of threads from all processes and picks the next one to run based on its algorithm like CFS or the Windows scheduler.
Exactly. This makes the kernel the ultimate arbiter of CPU allocation for all threads, giving it full control and visibility. It often simplifies the mental model for application developers too, since they're effectively interacting directly with kernel-managed threads.
Okay, let's shift gears now to a realm where timing isn't just about making things feel snappy, but about, safety and mission success. What about systems where missing a deadline isn't just an inconvenience, but could have severe, maybe even catastrophic consequences? I'm thinking about things like control systems in an airplane, critical medical devices like pacemakers, or maybe industrial robots on an assembly line. The stakes feel profoundly higher than just a slow web page loading.
You've perfectly captured the essence of real-time systems. These systems have far more stringent, precise, and often guaranteed scheduling requirements compared to the general-purpose operating systems we've mostly been discussing. We generally distinguish between two main categories. Hard real-time systems. These systems must complete critical tasks by an absolute guaranteed deadline. Failure to do so is considered a complete system failure, potentially leading to disaster. Think anti-lock braking systems in a car. A delayed braking response could be fatal. There's no room for error.
Okay, hard means deadlines are absolute.
Soft real-time systems. These systems prioritize real-time tasks and strive to complete them by their deadlines, but they don't offer absolute guarantees. Missing a deadline occasionally in a soft real-time system is undesirable, maybe degrading performance, but it's not necessarily catastrophic. A streaming video player is a good example. A slight delay might cause a skipped frame or audio glitch, which is annoying, but the whole system doesn't fail.
Right, soft means deadlines are important targets, but not life or death.
Pretty much. Now, the scheduler for any real-time operating system, hard or soft, must fundamentally support a priority-based algorithm, and crucially, it must be preemptive. More important, time-critical tasks are assigned higher priorities, and if a higher priority real-time process becomes ready to run, it will immediately preempt any lower priority process currently using the CPU, even if that lower priority process is another real-time task. Hashtag critical latencies. Now, to achieve these incredibly strict deadlines and guarantees, especially in hard real-time systems, the OS must aggressively minimize certain crucial latencies. These are bottlenecks that designers obsess over reducing to the absolute minimum.
More latencies to worry about. What are the key ones here?
Two are paramount. Interrupt latency. This is the time elapsed from the moment a hardware interrupt signal is generated, maybe by a sensor detecting a critical condition in a factory, to the very start of the specific code, the interrupt service routine, ISR, within the operating system that handles that interrupt. Real-time OCs demand this to be exceptionally short, often measured in microseconds or even nanoseconds.
So super fast reaction to external events.
Exactly. This imposes a strict constraint. The kernel can only disable interrupts for absolutely tiny, predictable periods. Disabling them for too long would block critical signals from being processed promptly, potentially missing a deadline. Dispatch latency. We discussed this earlier in the general context of the time taken for the scheduler to stop one process and start another. In real-time systems, this also needs to be minimal and, crucially, predictable.
Right, the context switch overhead again. How do they minimize that for real time?
The most effective technique here is to employ preemptive kernels. This is a big deal. It means that the kernel itself, even when it's executing its own internal code, like handling a system call, can be preempted by a higher priority real-time task if one becomes ready.
Wow, so even the OS code can be interrupted for a critical task.
In a truly preemptive kernel, yes. This ensures that the most critical tasks can seize the CPU virtually immediately without having to wait for the kernel to finish whatever it was doing. This significantly reduces dispatch latency compared to non-preemptive kernels, where a task might have to wait for a potentially long kernel operation to complete.
Okay, so given these incredibly tight constraints and the need for preemption, how do these systems actually decide which critical task gets to run when? Is there a common systematic way to assign those priorities to ensure deadlines are met, especially if they're static?
Yes, one of the foundational and widely studied approaches for hard real-time systems is rate monotonic scheduling, or RMS.
Rate monotonic. What's the rate part mean?
RMS assigns static priorities to tasks based on their periods, that is, how frequently they need to execute. The rule is beautifully simple. The shorter the period, meaning the higher the rate or frequency it needs to run, the higher its static priority.
So faster tasks get higher priority.
Yeah, seems logical. It is. It's a priority-based preemptive algorithm. If a higher priority task, one with a shorter period, becomes ready, it will immediately preempt any currently running lower priority task, one with a longer period.
Okay. Does it always work? Does it guarantee deadlines?
Ah, that's the crucial question. RMS is elegant, but it has limitations and doesn't always guarantee deadlines, even if the total CPU usage seems like it should be manageable. Let's look at a classic example, which our source material illustrates really well in Figure 6.8, showing exactly where RMS can fall short. Consider two periodic tasks. P1 has a period of 50 milliseconds and requires a CPU burst of 25 milliseconds each period. P2 has a period of 80 milliseconds and requires a CPU burst of 35 milliseconds each period.
Okay, P1 needs 25 meters every 50 meters. P2 needs 35 meters every 80 meters.
Under RMS, P1 has the shorter period, 50 meters versus 80 meters, so P1 gets the higher static priority. Let's trace the execution. Time is 0. Both P1, deadline 50, and P2, deadline 80, become ready. P1 has higher priority, so it starts. Runs for 25 meters, time 25. P1 finishes its burst. P2 is now the highest priority ready task, so it starts, time 50. P1's next period begins. Its new deadline is now 100 meters. Since P1 has higher priority, it immediately preempts P2. At this point, P2 has run for 25 meters, from time 25 to 50, out of its needed 35 meters, so 10 meters remain for P2.
Okay, P2 gets interrupted.
Time 50 to 75. P1 runs for its next 25 meters burst, finishing at time 75. Time 75, P1 finishes. P2 can now resume, needing its remaining 10 meters. Time 75 to 85, P2 runs for that final 10 meters, finishing its work at time 85.
Exactly.
Clear.
P2 finished at time 85, but its first deadline was at time 80?
Exactly. P2 missed its deadline, even though the total CPU utilization, 2550 plus 3580 plus 0.4375 is less than 100%, RMS failed to meet the deadlines in this specific scenario.
Wow, so RMS isn't foolproof.
No. This example from our source is a powerful illustration. RMS can fail even on systems that are theoretically schedulable. It has known utilization bounds. If the total utilization exceeds a certain threshold, which depends on the number of tasks, RMS might not guarantee deadlines. It highlights a fundamental limitation of static priority schemes in certain complex timing interactions.
So if static priorities, even when intelligently assigned based on rate like an RMS, can still lead to missed deadlines, is there a more dynamic, maybe more adaptive approach that offers better real-time guarantees, one that perhaps looks at deadlines more directly?
Yes, there is, and it's a very elegant and powerful alternative. Earliest deadline first, EDF scheduling.
Earliest deadline first. Okay, the name sounds promising.
It is. EDF is also a priority-based preemptive algorithm, but its priorities are dynamic, not static. Instead of being fixed based on period, the rule is brilliantly simple. The process with the earliest absolute deadline is always given the highest priority at any point in time.
So priorities change constantly based on upcoming deadlines.
Exactly. As deadlines approach, a task's priority effectively increases relative to others. This ensures that the most urgent task, the one closest to potentially missing its deadline, naturally gets the CPU.
That sounds like it should work better. Let's use the same P1 and P2 tasks as before. P1 period 50 burst 25, P2 period 80 burst 35, and see how EDF handles it. I think the source had figure 6.19 for this one.
Okay, let's trace it with EDF. Time 0, P1, deadline 50, and P2, deadline 80 arrive. P1 has the earliest deadline, 50 versus 80, so it gets the highest priority and starts running. Time 0 to 25, P1 runs for its 25 meters burst, finishing at time 25 it met its deadline. Time 25, P1 finishes. P2 is now the only ready task. Its deadline is 80. So P2 starts running, time 50. P1's next period begins. Its new deadline is now 100 meters, time 50 plus period 50. Now we compare deadlines. P2's current deadline is 80 meters. P1's deadline is 100 meters. P2 still has the earlier deadline.
So P2 doesn't get preempted by P1 this time.
Exactly. Because P2's deadline, 80, is earlier than P1's new deadline, 100, P2 continues running. Time 25 to 60. P2 runs for its full 35 meters burst, finishing at time 60. Time 60, P2 finishes. It easily met its deadline of 80 meters. P1, deadline 100, is now the only ready task. P1 starts. Time 60 to 85. P1 runs for its next 25 meters burst. Finishing at time 85, it met its deadline of 100 meters. Time 80. P2's deadline passes, but it finished way back at time 60, no problem. Time 100. P1's deadline passes, it finished at 85, no problem. The system then remains idle until the next task arrival or period begins.
Amazing. So EDF successfully scheduled both tasks to meet their deadlines in exactly the same scenario where RMS failed.
Correct. EDS is often considered theoretically optimal among dynamic priority schemes for single processor systems. It's proven that if a set of periodic tasks can be scheduled to meet all their deadlines by any algorithm, then EDF will successfully schedule them.
That's a powerful guarantee.
It is. This makes EDF a widely adopted and very important algorithm for designing complex real-time applications, offering greater flexibility and often higher achievable CPU utilization compared to static priority systems like RMS.
Okay, this is where the rubber really meets the road, right?
Hmm.
We've laid out all these conceptual frameworks, SCFS, SJF, priority, round robin, multi-level queues, RMS, EDF. But how do the big players, the operating systems we use every single day, like Linux and Windows, actually implement these sophisticated ideas? How do they mix and match them to keep our computers running smoothly across such varied tasks?
That's right. Each major operating system has definitely developed its own highly sophisticated, often quite unique approach to CPU scheduling. They frequently combine elements of these classic algorithms we've discussed, but then layer on specific heuristics, dynamic adjustments, and unique innovations to try and strike that difficult balance between performance, fairness, and responsiveness across incredibly diverse workloads and hardware configurations.
I often hear Linux's scheduler, especially the completely fair scheduler, or CFS, praised for being particularly elegant or advanced. What's its secret sauce? How does it achieve that balance of fairness and performance that people talk about?
Yeah, Linux 2.6 introduced the Completely Fair Scheduler, CFS, and it really was a radical and highly significant overhaul from the earlier, more traditional UNIX style schedulers Linux used before then. CFS truly prioritizes fairness above almost all else, but it does so in a fundamentally different way. It avoids explicitly assigning static priority numbers in the traditional sense, which is quite clever.
No priority numbers. How does it prioritize then?
The core ingenuity of CFS lies in how it tracks a value called virtual runtime, or runtime, for each task or process. Think of runtime as a measure of how much CPU time a task would have received if the CPU were perfectly fair and infinitely fast.
Okay, a virtual clock for each task.
Sort of. This runtime accumulates based on how long a task has actually run on the CPU. But, and this is the crucial part, this runtime accumulates slower for higher priority tasks and faster for lower priority tasks. Or you can think of it as decaying faster for lower priority tasks.
So higher priority means your virtual clock ticks slower.
Effectively, yes. It's weighted by the task's niceness value, Linux's way of expressing priority. So a high priority task's runtime grows more slowly, making it appear younger in terms of CPU usage compared to a low priority task that ran for the same actual amount of time. The scheduler's job then becomes incredibly simple. It just picks the task with the smallest current runtime to run next.
The youngest task in virtual time gets to run.
Exactly. This elegant mechanism automatically ensures that tasks that have waited longer and thus have a relatively smaller runtime compared to tasks that ran recently, or considered higher priority because their runtime naturally accumulates slower, get their turn sooner.
That's fascinating. It achieves fairness and priority implicitly through this virtual time concept.
Right. And it's a fully preemptive scheduler. If a task wakes up or a new task arrives with a significantly smaller runtime than the currently running task, the current task gets preempted. It creates this highly dynamic, adaptive system where every process feels like it's getting a fair share of the CPU over time, aiming for that ideal of perfectly distributed processor time.
That is a really neat way to do it. It's like a perpetual race where the slower runners, the lower priority, get a virtual head start or run on a faster clock to ensure they keep up in the runtime race.
That's a good analogy. And this philosophy extends beyond just CPU scheduling in Linux. For I/O scheduling, particularly for traditional spinning disks, Linux also employed the completely fair queuing CFQ I/O scheduler for a long time. Instead of just one big queue for all disk requests, CFQ maintains separate request lists for each process doing I/O.
Fairness for disk access, too.
It would then service these queues in a round-robin fashion, ensuring fairness and preventing one I/O-heavy process from monopolizing the disk while others starved for data. While modern SSDs often use simpler I/O schedulers now, CFQ showed that same commitment to fairness across different resource types. Hashtag Windows scheduling.
Okay, what about Windows? It's used by billions of people every day, often for very demanding interactive tasks like gaming, video editing, complex office work. How does Windows manage to keep everything feeling so responsive amidst all that?
Windows uses a different but also very sophisticated approach. It employs a multi-level priority scheme, typically with 32 distinct priority levels.
32 levels, okay.
Right. Priorities 16 through 31 are reserved for real-time processes. These get the highest precedence to ensure critical system tasks or specialized real-time applications meet their deadlines, much like the concepts we discussed earlier. Most regular user applications and threads operate in the variable priority class, which usually spans priorities 1 through 15.
Variable priorities, so priorities change.
Yes, and this is key to Windows responsiveness. Windows scheduling is particularly interesting for its dynamic priority adjustments, aimed squarely at optimizing the interactive user experience. It uses that variable priority class for most threads. When a thread runs for its entire time quantum without blocking, its priority is generally lowered slightly, though never below its initial base priority. This acts as a mechanism to gently penalize CPU-bound tasks, preventing them from continuously hogging the processor at their base priority.
Okay, CPU hogs get slightly deprioritized over time.
Conversely, and this is a crucial insight for making things feel snappy, threads that are released from a wait operation get a priority boost. For example, if a thread was waiting for keyboard input, mouse clicks, network data, or a disk operation to complete, when that wait finishes, its priority is temporarily increased.
Why boost them?
The logic is brilliant. If a thread was waiting for user input or I/O, it likely needs immediate attention when that input or data finally arrives to update the UI or process the data quickly. This strategy provides excellent response times for interactive applications and I/O-bound tasks.
Ah, so the things you're actively waiting on get a boost when they're ready. Makes sense.
There's even a special, though temporary, priority boost given to the threads associated with the active window, the application window you're currently interacting with. This further enhances its perceived responsiveness and makes your current task feel smoother.
Clever tricks to prioritize what the user is likely focused on.
Exactly. Furthermore, as hardware has evolved with more and more CPU cores, Windows has adapted. Windows 7 introduced processor groups to allow the operating system to scale efficiently beyond 64 logical CPU cores, addressing the needs of high-end servers and workstations. It also features user mode scheduling, UMS, which is interesting. It allows certain programming language libraries, like Microsoft's concurrency runtime for C++s, to implement highly efficient user mode schedulers for managing fine-grained tasks within an application. This gives developers more control over scheduling very lightweight tasks, potentially reducing kernel transitions and overhead for specific parallel workloads.
So apps can do some of their own scheduling.
In a controlled way, yes, using UMS. Finally, another important internal detail is how Windows manages many kernel mode synchronization primitives, things like semaphores, mutexes, events, processes, and threads themselves as dispatcher objects. Threads can block efficiently inside the kernel dispatcher, waiting for these objects to be signaled, for example, waiting for a mutex to be released. This provides a robust and unified mechanism for thread synchronization and coordination deep within the kernel.
This is fascinating stuff. For those listeners who maybe really want to roll up their sleeves and get their hands dirty with OS development or just deeply understand the raw mechanics, I know teaching operating systems like Pintos offer a unique window. What can looking at a simpler OS like Pintos illuminate about scheduling that might be harder to see inside the complexity of Linux or Windows?
Pintos is a fantastic tool for that, absolutely. It's a simplified operating system framework designed for the x86 architecture, primarily used in university operating systems courses. It supports kernel threads and a basic scheduler, but its real brilliance lies in being simple enough for students to actually read, understand, modify, and extend. You can really see the nuts and bolts.
So what are some key scheduling takeaways from Pintos?
Here are a few crucial learning points that Pintos makes very concrete. First, the absolute core of context switching, saving, and restoring the raw CPU state, registers, instruction pointer, stack pointer, is handled in low-level assembly code. In Pintos, it's in a file often called thread switch. This immediately teaches you that this critical operation is extremely hardware dependent and needs to be meticulously optimized for speed.
Could speak the CPU's language directly there.
Second, what's conceptually really cool and sometimes mind-bending when you first see it is tracing how a call to the context switch function, like switch threads in Pintos, can actually return execution in a completely different thread later on.
Wait, how does that work?
Well, thread A calls switch threads to yield. The scheduler picks thread B. Thread B runs for a while. Eventually, the scheduler picks thread A again. It restores thread A's save state, including its instruction pointer, which was right after the call to switch threads. So from thread A's perspective, it looks like the switch threads function simply return, but potentially milliseconds or even seconds later, and the whole world might have changed. It elegantly demonstrates that fundamental remapping of CPU control.
That really shows how threads share the CPU. Wild.
Third, the scheduler in Pintos is initially kicked off by a function like thread start. In a time-sharing setup, which students often implement, the scheduler is then triggered repeatedly by a timer interrupt, handled by a function like thread tick. This function keeps track of time slices. If a thread slice expires, Thread tick flags that a reschedule is needed, demonstrating preemptive scheduling at a very basic, tangible level. Fourth, after a thread switch actually happens, there's often a specific cleanup function, like thread schedule tail in Pintos, that runs in the context of the newly switched to thread. This handles crucial tasks like freeing the memory stack of a thread that has just finished executing a dying thread.
Why does the new thread clean up the old one?
Because the dying thread stack is still in active use by the CPU right up until the moment control is fully transferred to the new thread. You can't pull the rug out from under yourself. It's a subtle but vital detail in safe OS design.
Ah, okay. Gotta wait till you're safely off the old stack.
Fifth, Pinto strongly emphasizes the importance of avoiding busy waiting. That's when code sits in a loop, constantly checking a condition and consuming CPU cycles while just waiting for something to happen, like, wow, do nothing. This is hugely wasteful. Instead, threads should use proper synchronization primitives like semaphores or condition variables to block or sleep efficiently until the event they're waiting for actually occurs. This allows the CPU to be productively used by other ready tasks.
Don't spin, just sleep.
Exactly. Sixth, Pintos assignments often highlight challenges like handling page faults, accessing memory that needs to be loaded from disk, which inherently requires slow I/O operations. The system needs to handle this interruption gracefully, block the faulting thread, schedule another thread to run, and then resume the original thread once the data is loaded from disk. This underscores the deep need for careful synchronization, interrupt handling, and integration between memory management and scheduling. And finally, as a practical simplification, the base version of Pintos often doesn't save or restore the floating point unit (FPU) state during context switches. This means, in that simple version, you generally can't use floating point math in user programs because the FPU registers would get corrupted when the OS switches between threads.
Oh, wow.
It serves as a great lesson on the many subtle details and trade-offs involved in building a full-featured OS. Saving restoring the FPU adds overhead to every context switch, so maybe you only do it if a thread actually uses the FPU. It forces students to think about those complexities. Hashtag tag, hashtag outro. So we've covered a lot of ground today. We journeyed from the very basic coffee shop line analogy of first come, first serve, explored the theoretical optimum of shortest job first and its practical preemptive cousin SRTF, looked at priority scheduling and aging, then round robin, the multi-level queues, all the way to the sophisticated fair share algorithms like Linux's completely fair scheduler.
Yeah.
And then we dove into the deadline-driven precision needed for real-time systems with RMS and EDF, and finally saw how giants like Windows blend these ideas with clever heuristics for responsiveness. What truly stands out to me is just the constant innovation and the intricate engineering needed to keep balancing efficiency, responsiveness, and fairness across such incredibly diverse computing landscapes.
Absolutely. It's really incredible when you stop and think about the layers upon layers of complexity humming away behind every single click, every keystroke, every application running smoothly on your device. From managing those tiny CPU and I/O bursts to preventing starvation for background tasks and ensuring that life-critical systems meet their absolute deadlines, CPU scheduling is truly the unsung hero keeping our digital lives seamless and productive.
It's definitely not magic.
No, it's brilliant, adaptive design, constantly evolving to meet these ever-increasing demands we place on our systems. So what does this all mean for you, our listener? Well, next time you find yourself effortlessly multitasking, maybe playing a graphically intense game while downloading a huge file in the background and chatting with friends all at the same time, hopefully you'll have a much deeper appreciation for the intricate, beautiful dance happening beneath the surface, the scheduler orchestrating every single operation.
And maybe here's a final thought to mull over as we wrap up. As our systems become even more complex, think about the explosion of multi-core processors, heterogeneous architectures mixing CPUs and GPUs and specialized AI chips, the rise of cloud-native distributed applications. How might the very definition of fairness or optimality in CPU scheduling continue to evolve?
Good question.
What new ingenious algorithms and techniques will operating system designers need to invent to manage these unprecedented challenges? How do you schedule fairly across not just cores, but across different types of processing units, or even across different machines in a cluster? It's a problem space that definitely never stops demanding innovation.